Okay, so I'm going to start with some announcements and then start the lecture. For those of you who haven't, and it looks like that's a large group of you, I had mentioned that we will use Piazza discussion forums to have this online discussions of labs and so on. So there, I added a link. Very few of you signed up. Okay, so I went ahead and added a link from the Moodle page to Piazza. So if you click there, it will take you to the discussion board. If you don't have an account, you need to create a free account. If you have an account, you need to say you're taking this class, so it will add you to the class. Okay? Otherwise, you cannot see any posts and whatnot. So please go ahead and do that. That way, you will see anything that is getting posted. Okay. Okay. So we are going to talk about processes and threads today. But before we start, I am going to start with a computing parable. Every once in a while, I will tell you a story which will have a moral. Today's story has to do with the lion and the rabbit. Okay, the story is as follows. So there's a rabbit in the forest, and um, the rabbit is doing some work, and a fox comes along. Okay, and then the fox asks the rabbit, "What might you be up to?" And then the rabbit says, "I'm writing a paper, and the title of the paper is that rabbit can eat foxes." Okay, and then the fox says, "That's utter rubbish. Everyone knows rabbits cannot eat foxes." The rabbit says, "Let me prove it to you." Okay, and takes the fox into a cave and comes out, and then there is no sign of the fox. Okay, and then a few hours later, a wolf comes along and sees the rabbit, and he asks the rabbit, "So what's going on?" And the rabbit says, "I'm working on an exciting paper. It's titled Rabbits Can Eat Wolves." Okay, and the wolf says, "That's utter rubbish. Nobody knows. Everyone knows that you cannot have rabbits eating wolves." And then the rabbit says, "Let me show you." He takes the wolf into a cave, and then the rabbit comes out a little while later. There's no sign of the wolf either. Okay? And then later, the rabbit goes back into the cave, and inside the cave, there is a lion. There's a pile of bones, and the lion has essentially eaten both the fox and the wolf. Okay, so that's the story. Now, what's the moral of the story? The moral of the story is, in this case, the rabbit is actually a student, and the lion is the advisor. And the moral of the story is it doesn't matter what topic you pick for your thesis or papers, what matters is who your advisor is. So choose your advisor well is the takeaway. Okay? And we will have another one that's analog next week. Okay? So let's start. I'm going to switch gears. We were talking about architectures for distributed systems. This is going to be the first real topic for the class. Today's lecture is going to be part refresher, okay, and part new material, because we are going to start with processes and threads today. Some of this is material that you cover in an undergrad class. So if you have taken an undergraduate OS class, some of this will be repetitive, but bear with me. We need this background to build up, okay, when we get to multiprocessor scheduling, distributed scheduling, virtualization. It's essential that we have a common understanding of what processes and threads are, and many of you already know this, and I'm just going to review that material today. And then for the later part of the class, we'll talk about some more interesting stuff that you probably have not seen in an undergraduate. Okay, so let's start with processes. This is simply a review. Okay, so these are things you should know. Okay, if you are not familiar with it, take a look at any undergraduate textbook, okay, in operating systems. Read it quickly. You don't have to know it in a lot of detail. It's just terms that if I mention them, you should at least know what I'm talking about. Okay, so just something you need to be familiar with. So there is this notion of multi-programming versus multi-processing. Multi-programming just says that you have the ability to run more than one program and hence more than one process in your system at the same time. Or concurrently, today most operating systems are multi-program systems. They allow you to run more than one process at the same time. Okay? Multi-processing simply says that you have more than one processor, and hence you have the ability to run more than one process in parallel. Okay, so multi-core systems are examples. So most of the machines you buy today have more than one core. Even your phone might have dual core or quad core, and laptops and all of them have the same features. So if you have more than one core, you have the ability to run more than one process in parallel. Okay, process A is run on core 1 and process B on core 2. Okay, in multi-programming, you have more than one process active, but you may have a uni-processor or a uni-core system, so they have to take turns to run. Okay, so it's not true parallelism, it's concurrency. Multi-processing gives you true parallelism. Okay, that's something to keep in mind. One data structure that you will need to actually know about is a kernel data structure that is used to track all the processes that are active in the system. Okay? The OS is responsible for resource management on your machine. It has to allocate resources to processes. Okay? And it has to track which processes are active, what kinds of resources are they accessing, how much RAM has been given to them, how much CPU time they've taken. All of that is tracked in kernel data structures. Okay, if you read an undergrad textbook, that data structure is referred to as the process control block or the PCB. Different operating systems have different terms for this data structure. Okay, we'll just use PCB as a canonical term that encompasses all these data structures. Okay. Now, having said that, we should also understand what is a process. Okay, typically, a process will have what is referred to as an address space. That's the region of memory it can address. Okay, typical layout of a process. I'm going to show you a logical layout for process. Okay, let's say this is the memory view of a process A. Okay. Typically, a process is going to have some segments associated with it. Okay. Most processes have at least 3 segments. Most of them will actually have more than 3, but at least 3, which is referred to as code S segment, there's a stack segment, and there's a heap segment. Okay. The code segment is where the code for that process resides. Any code that you write eventually turns into machine code. Okay. Assembly instructions and then machine code. The machine code is actually resident in memory in what is called the code segment. Okay. It's also referred to as a text segment in some cases. Okay. That's the code. Okay. Our process is going to have some variables associated with it, some data structures associated with it. Those would either be stored in the stack or the heap. Okay. Heap is dynamically allocated memory. Okay. Dynamically allocated structures go in the heap. If you run malloc or new or anything like that, it's going to go in the heap. Any statically allocated data structures, local variables, global variables, they will go in the stack. Okay. Most of the times there will be other segments associated with the process for things like synchronization and other things, but you should at least know that there are 3 important. Okay, the stack, heap, and the code segment. Okay. Any questions on that? Okay. So that's what a process looks like from an address space perspective. Okay. A process over its lifetime is going to go through many different states. The state of a process describes what that process is doing at any given point in time. Okay. There are several states that a process will transition to. Whenever a process starts up, it starts up in the new state. A new state simply says that the process is still being set up by the OS. It's being loaded by the OS and it's setting up data structures and so on. Okay. Once the process has been loaded in memory, okay, it is going to transition to what's called a ready state. Okay, ready basically tells the OS that the process is now ready to run. It's not yet running on the CPU, it's just ready to run. Okay. Eventually, the CPU, through its CPU scheduling mechanism, will actually choose this process to execute. Okay. And at that point, it will transition to a running state. Okay. Run essentially means actually executing on the processor. Okay. It's actively executing. Okay. So from this state, you may even, if the process does I/O, it's going to go into a wait state. Okay, while it's executing, let's say it tries to do some I/O, tries to read some data from file, tries to print something to the screen or some such thing. It's going to go to a wait state where you will wait for the I/O to finish. The process will be blocked until the I/O is finished. Okay? And once the I/O is done, it will go back to the ready state and then eventually it will get to run again. Okay? Now, if a process is CPU bound, it does not do any I/O while it's running and its, let's say, time slice expires, it will just go back to the ready state and cycle between. Okay, so it's going to cycle between these 3 states over its lifetime, and eventually when it's done, it's going to go into a terminate state. Okay? So that's basically a life cycle of a process, just something to know. We're not going to go into any detail as far as that is concerned, but something you should know that you will basically have a computation and IO, okay, over the life cycle of a process. If you're CPU bound, you will mostly be doing computation. If you're IO bound, you'll spend most of your time doing IO. Over your life cycle of a process, you may actually be CPU bound or IO bound at different points in time. This is something to keep in mind. Yeah. Those are process transition states. Okay. Let me talk a little bit about scheduling algorithms, because starting next time we are going to start building on what you learn from a uniprocessor scheduling standpoint. We look at multiprocessor and distributed scheduling. Okay, so it's good to at least know or recap what uniprocessor scheduling means. Okay. Typically, there is, as I said, if you have a multi-programmed system, you have more than one process that's resident or active in your system at any given time. Okay. So let's take a scenario where many processes are all ready to run. Okay. And the OS has to decide which one actually gets to run. Okay. If you have a single core, only one of those ready processes will run at any given time. Okay. We will have a notion of a time slot or time slices. So each process, when it's chosen to run, is going to be given a time slice. When its time slice expires, we will have a context switch. We'll save the state of that process and then pick another process. Okay? The policy that is going to decide which process from the ready queue gets to run is the CPU. It's called CPU scheduling. Okay? That's a CPU scheduling policy. Okay? In the uniprocessor world, there are several of these policies, and you will see that the same is true of multiprocessing and distributed scheduling, which we will talk about next time. But let's just go through a few of these. Okay? So round robin. Okay? The simplest one is, of course, FIFO, first come, first serve. Okay? You essentially have a queue here. So this is referred to as the ready queue. Okay, and processes are queued up here. Okay, they're all ready to run. First come, first serve just says take the first one from the queue, let it run. Okay, and this is not even going to use time slicing. This is a non-preemptive policy. You just let it run to completion. Okay, and then you pick the next one, let it run to completion, and so on. Okay, that's FIFO. That's the simplest of the policy. Okay. What round robin does is it uses this notion of time slices. So you will pick A, you will run it on the CPU, and you'll give it a certain amount of time. It's called a time quantum. Let's say it's 200 milliseconds, a typical quantum used in Linux. Okay. So the process will run for 200 milliseconds. If it hasn't done I/O by then, it will basically be asked to give up the CPU. If it does I/O in the midst of its quantum, then its quantum ends automatically. And the next one runs. So you'll cycle from A, B, C, D, and then keep doing this. Okay? So this is round robin. So you're going to cycle through them in round robin fashion. Okay? Fairly straightforward. Shortest job first says that suppose you had this ready queue and you knew the job lengths. You pick the shortest one and run it. Okay? So you will basically require to implement shortest job first knowledge of the job lengths, which is how long is the process, how much computation time does it need until it finishes, and then you pick the shortest of the jobs and you run that first, and then the next shortest job, and so on. Okay? As you will remember from any undergrad class, shortest job first policy is optimal in terms of waiting times. Okay? It minimizes the average waiting time in the system. And by picking the shortest job and finishing shorter jobs first, it reduces the waiting time. And the intuition is if you actually had picked a long job, other jobs have to wait for a longer period of time before they get to run. So if you go with the shorter jobs, then you're reducing the overall waiting time in the system. Okay. At the same time, shortest job first is not a very practical policy because it requires the OS to know about the length of a job. Okay. Typically, when you start a process, the OS has no knowledge of how long this application is going to run. It's up to the user. And you might start a browser. How is the OS to know how long are you going to keep the browser open? You can close it at any time. You can do whatever you want with it. So job lengths are not practical to infer or know in a system. So as a result, it's not a good policy you can actually implement easily. Okay? Maybe only in very specialized circumstances. Okay? So that's shortest job first. Yeah, the last two are more specialized policies. Lottery scheduling is a randomized policy. Okay, so Essentially, what lottery scheduling does is it allows you to assign what are called lottery tickets to each process. Okay. Now, all the processes in the ready queue are going to run a lottery. Okay, they're all going to put their lottery tickets in a hat. You pick a winning ticket. The process that holds the winning ticket actually gets to execute next. Okay, completely randomized. So let's say if you give one ticket each to A, B, C, and D, okay, one lottery ticket, the probability of winning the lottery is 25%, 1 over 4. Okay, so in a randomized world, one of them is going to win the lottery. You keep doing this, or on average, you will get 25% of the CPU time because you will win the lottery 1/4 of the time. Okay, the user can control the number of lottery tickets you assign to processes. Okay, and thereby also control how much CPU time they get. Okay, so for example, if there are only two processes, let's say A and B, and you gave two lottery tickets to A and one to B, okay, you can compute the probability each of them is going to win the lottery. Okay, what's the probability of A winning lottery?
2/3.
2/3. Okay. This is 1/3. Essentially, the probability of winning the lottery is the number of tickets that are given to process I over the total number of tickets in the system. Okay, so that's basically the probability you'll win the lottery. Yes, question. Sorry?
This is non-preemptive.
Yes, everything other than first come, first serve and shortest offers, everything is time sliced and hence preemptive, not non-preemptive. Okay? So you basically win the lottery, you will run for a time slice and then you will rerun the lottery. Okay? Any other questions? All right. So that's lottery scheduling, and then the last one is called EDF, earliest deadline first. This one is a specialized scheduler that's used in what are referred to as real-time systems. Okay? In this case, each process has a deadline associated with it. The deadline indicates the time by which the process needs to finish a task. Okay? And then the scheduler is simply going to pick a process in earliest deadline first order. Okay, that's why it's called EDF, earliest deadline first. Okay, this is used in very specialized scenarios. You want a task to complete by a certain time, and you want a guarantee. Okay, most of these others are referred to as best effort schedulers. Okay, they don't give you any guarantee. So you might ask, what are scenarios where you need a task to finish by a certain deadline? Okay, there are many systems where this might be true. Okay, think of playback of an audio or video file. Okay? If you do not play back video image by a certain time, your playback will freeze. Okay, you basically, let's say playing back a video clip over YouTube or whatever. If you don't receive the data and you don't play it out, your playback it just freezes. Okay, and then it starts after some time a new data. So that's a scenario where there are timeliness constraints associated with your task. Okay? Or think of a car where a microcontroller needs to activate an airbag. Okay? If there is a sensor that detects that there is a collision, you want to activate the airbag very quickly, okay, in a guaranteed amount of time for safety reasons. You can't just say activate airbag, run that procedure and wait for some period of time, because that does not work from a safety perspective. So there are many mission critical systems where you will actually see earliest deadline first being used as opposed to some of these more general purpose schedulers. Okay, so that's EDF. Yeah, now I do want to mention that the choice of a policy, okay, there's no policy that's always going to be the best one, okay, for all scenarios. Okay? Depending on the scenario, depending on the workload and the system, different policies might be appropriate. And the way you are going to decide is you are going to say what metrics do you care about or do your users care about. Okay? Is it that you want high throughput in your system? You want high CPU utilization? Okay? You want low turnaround time? So you want interactive system with high responsiveness or low response time? Or you want fairness that treats all processes fairly? Okay? These all sound like good things to achieve in a system. Okay? You want to say, why not have high throughput and high utilization and low response times and good fairness? Okay? But the problem is you can't do it all. Okay? If you try to make one metric better, it's always at the expense of some other metric. So in some sense, you will have to decide which of those things do you care about as a system designer for your system, and then optimize for that metric, which will mean that some of these policies will become more desirable than others because some of them optimize certain metrics and others will optimize other metrics. Shortest job for optimizes waiting time, okay? But makes some other metrics worse and vice versa. So you will have to decide based on the goals for your system which one to use. Okay. Any other questions here before I move on? Okay. So let's review for processes. We'll talk a little bit about process behavior. So processes, as you look at the lifetime of a process, you will see that they alternate between CPU and I/O. Okay, so you might do some computation, go back to doing I/O, go back to doing computation, and so on. And if you look at the CPU times, times for which you perform computation and times of which you do I/O, and try to model it, you're saying what do process CPU times look like? You will see that the process behavior looks like this. There are often CPU bursts. Okay? In many cases, the bursts are short, okay? And then you do some I/O. But in some cases, you might have long computation. Let's say you enter a loop in your program, and the loop requires you to execute quite a few iterations. Okay? That's a longer computation. Or you might be doing lots of I/O. You do a little bit of computation, and then you go back to doing I/O. Okay? So you will, if you empirically or experimentally trace the behavior of a process and look at whenever a process is doing computation, how long is the time for which it did computation before it went back to doing I/O, and then you look at those times and model them as a distribution, probability distribution. It has been observed that you can actually use what is referred to as a hyper-exponential distribution to model it. And this is a picture that shows you a hyper-exponential distribution. So you will see that there is a bump for short bursts, which says that many bursts, when you start doing computation, many bursts are likely to be short, and then you go back to doing I/O. But there's also a long tail for this distribution, which says that every once in a while, okay, infrequently, you will have a long CPU burst where the process goes into doing a lot of computation before it reverts back to doing some I/O. So this is what has been observed experimentally for about process behavior. This is average on an average. This doesn't say that a given process has to behave exactly this way. But if you look at a large collection of processes and model their CPU behavior, computational behavior, you will see that it can be modeled as hyper-exponential distribution. Now again, I don't expect you to actually know a lot more than just understand that there are distributions that will explain process behavior in the aggregate. Okay, that's all you really need to know. In fact, I'm not even going to go into the definition here. That's the definition of a hyper-exponential distribution. That's exponential, which we are going to ignore here. Okay? So just keep this in mind, that process behaviors are hyper-exponential, which essentially says the common case is short CPU bursts, but occasionally there'll be long CPU bursts. We'll come back to what this means for system design later. Okay? What do you have to do to ensure that long bursts are handled efficiently and so on. Okay? Okay, so now let's talk a little bit about priority scheduling, and I'm going to talk also about a scheduler that you may have encountered in an undergraduate course as well, called multi-level feedback queue or MLFQ. Okay, so in many systems, what you will see is you can have priorities associated with processes, which tells the OS what is the importance a user has assigned to that process. Okay, and the idea is more important processes get preferential treatment as far as CPU scheduling goes. If there are two processes that are both ready to run, one has a higher priority than the other process, then the CPU scheduler is going to prefer or choose the higher priority process to run. This is referred to as priority scheduling. Okay, so in many cases, you will have multiple priority levels associated with the process. In fact, in most operating systems, you can actually change, the user can change the priority level associated with your process. Okay? By default, when you start a process, it gets a default priority level. But if you believe that some process is more important than the other, you can increase its priority. Okay? Examples may be kernel tasks, okay, can run at a higher priority than user tasks, because operating system tasks are important. You don't want to delay them. If something has happened, you might want to execute the kernel task immediately. So the kernel processes or system processes might get by default higher priority than user processes. That's one policy you can assume. Even within user processes, you can think of some tasks that have higher priority than other tasks. Okay, let's say you are going to do a Skype call. Okay, and you are running a background computation. You're running MATLAB in the background and just doing some computation. Okay? You don't want a computational task in this case to impact running of Skype, because if your Skype call does not get the CPU time that it needs, then your call is going to keep breaking up. Okay, because it cannot run, it cannot put the audio onto the speakers, and then you cannot hear what's going on. It's not capturing something. So you don't get good performance for your application if you do not actually get the CPU time it needs. So you could actually put audio tasks or video tasks at higher priority. That's commonly done in some systems. Okay? How you choose priority is not important. What's important to know is most operating systems support the notion of priority for tasks, okay, and then implement a prioritized scheduling that gives higher priority to tasks with higher preferred tasks with higher priority. Okay. I'm going to now show you one scheduler that actually does this dynamically. Okay, priority scheduling. It's called multi-level feedback queue. Okay, this is something that you might have, as I said, encountered in undergrad class, but let me recap what it does. Okay. So, a picture, which is essentially that picture. Okay. So that's your CPU. As the name suggests, in a multi-level feedback queue, you don't have one ready queue, you have n ready queues, more than one. Okay? And moreover, they have priorities associated with them. The top queue has the highest priority, the bottom queue is the least priority. Okay, so let's just number them by priority. This is priority 1, priority 2, priority 3. Okay? If there are tasks in more than one queue, anytime the CPU scheduler runs, it starts with the highest priority queue and says, is that queue empty or not? If it's non-empty, then it's going to do round robin at that queue. Okay? If it's empty, then you are going to go to the next queue and say, let's say this queue is empty, saying, is this queue empty or not? Okay? If it's non-empty, you do round robin at that level. If not, you keep going. So keep going down until you find the highest priority non-empty queue and you schedule tasks from that queue. Okay? This is priority scheduling. Any priority scheduler will do the same thing. It will say, are there tasks at the highest priority level? If yes, you're done. You find one of those tasks run. If you say no, then say, is there a task at the next highest priority level, and keep going down. Okay? So this is what multi-level feedback queue does. Okay, now I'll explain to you how you decide which task goes to which priority level. Okay? Whenever a new process is started up, okay, when you start a new application, say, it will join the queue at the highest priority level. So you start here. Okay. Now, when it gets to run, it's going to be given a time slice. Okay, the CPU scheduler will then observe what did the process do during its time slice. If it used up its entire time slice, okay, it's going to reduce its priority level by 1. Okay. If it did some I/O in the midst of its time slice, it's going to increase its priority level by 1. That's a rule it's going to follow. The rule is, whenever any process runs, doesn't matter which queue they came from, you observe what it does during its time slice. If it computes for throughout its time slice and uses the entire slice, you reduce its priority by 1. Okay? And on the other hand, if during its time slice it starts doing I/O, then you will increase its priority level. Okay, that's a rule that we are going to use for MLFQ. The question is, what is that going to do to processes in the system? Okay? Which kinds of processes are getting favored? What happens to these processes in terms of which queue they end up with, and so on. Okay, so let's try to understand the behavior. Okay? So based on this rule, what might you be observing?
Heavy computational processes get put at the bottom.
Okay, so computational processes are CPU bound processes are going to drop in priority. Is it clear why?
Because
Yes.
IO bound processes can like run in the background. So like if you give them priority, like the CPU requirement is less, so that finishes early, and then they can like in background they can do IO.
Okay. You are explaining the rationale for why that rule makes sense. That's a good thing. Okay, so you are 2 steps ahead of what I even asked. I was simply asking what is going to happen to IO bound and CPU bound tasks, and the comment made here was CPU bound tasks are going to drop in priority. And I was simply asking, is it clear that they are going to drop, or do you want me to explain? Because the rule says if you actually use up your entire time slice, you are going to drop in priority. That's the rule. Okay. You should ask what is a CPU bound task likely to do. If it's given a time slice, it's going to run through its time slice. By definition, it's CPU bound. It doesn't do IO. Okay. So it's going to use its time slice. Okay. That means its priority will drop. So if you start here, it will drop here. Eventually, it goes here. It will keep dropping until it hits bottom. Okay. And the IO bound tasks will be opposite. Okay. IO bound tasks are highly likely to do a short amount of CPU and then go back to doing IO. So it's very likely that during its time slice they will execute an IO instruction and go back to doing IO, and your time slice will not get used up. So you'll keep rising in priority. So IO bound tasks end up here. CPU bound tasks end up here. Okay. So that is what we have. Our priority scheduler has implicitly, based on this scheduling rule, given priority to IO bound tasks. Okay. The next question would have been, why is that the right thing to do? And that is what was actually answered, which was IO bound tasks are tasks that have short CPU duration. They do spend most of their time doing IO. Okay. So if you have a task that needs a small amount of CPU, okay, and a CPU bound task that needs a large amount of CPU, why not just run this small job, give it its CPU time, and have it go back to doing IO where it can make IO progress and then focus on the CPU bound task. This way, the IO bound tasks make progress and the CPU bound tasks also make progress when there are no IO bound tasks. Okay? So having higher priority for IO bound tasks is actually a sensible thing to do, because it's approximating shortest job first, as you will see. Because IO bound tasks are the ones that are short bursts. Okay? CPU bound tasks are the ones that are long bursts. So you give higher priority, you just give them whatever small CPU time they need. They go back to doing IO. They are no longer in the queue, they are in the wait queue. And then you can go back and execute your CPU bound tasks which need longer CPU times. Okay? That's multi-level feedback queue. It's a scheduler that is used by most Unix-like operating systems. Can you put your phone on? We don't have a device policy. Okay. So that's basically what is happening here. Lower priority to CPU bound tasks, round robin to each level, and higher priority to IO bound tasks. Okay. And if you look at a standard Linux FreeBSD Unix scheduler, you will see some instantiation of this. Any questions here? This is still, we are in review mode. So I'm going to pick up
How does it
pace.
switch between queues? Like for example, it can continue running the queue with priority one.
Okay. Question is, how do you switch between queues? It's a strict priority scheduler. You will always go to the highest priority queue that is non-empty and just run. You are asking if the Q1 is never empty, what happens? If Q1 is never empty, you will get starvation because you will never actually schedule anything below. Okay? So this technique does suffer from a potential starvation problem, where if there are a lot of IO bound tasks and there's something that's always ready to run, then your CPU bound tasks that are sitting there will never get CPU time. Okay, so you have to address that. The question again.
So what if a process quickly shift between CPU and IO?
What if the process quickly shifts between CPU and IO? That's okay, because while you're doing CPU, you will be here. There's nothing that says a CPU bound task cannot do IO. If it starts doing IO, then it will start rising in priority. It will start getting treated. You always treat a task what it is doing now. Okay? It may have been a CPU bound task in the past, now if it's IO bound, you will treat it accordingly. Okay. Any other questions here?
When it goes into an IO state, like it's doing IO computation, the build process go to a wait state or will still be running?
Yeah, if you are in IO state, you don't run, you block. So these are all ready queues. There's a separate queue that I said, which is all IO wait queues. So if you are anywhere here and you do IO, you're taken out of the ready queue, you go there. and then you just sit there waiting for your IO device to finish. Once you're done, then you will come back and rejoin these queues. Okay, so these are actually ready to run processes. They are ready to execute. Okay. Yes.
Suppose I have an application which is CPU oriented,
Hmm.
and is it advisable to have some IO step to improve the priority of that?
Oh. So question is, if your CPU bound task, should you insert IO to change its priority? Typically, this is not something the user has to deal with. The OS is managing this for you. Okay? If you explicitly want to give higher priority, you can change the priority level. These are default priorities that the CPU is managing, or the OS rather is managing on behalf of the process. If you believe something is more important, you should explicitly do that rather than change the code. Okay. Now that is not to say that if there is starvation, the OS cannot deal with it. If it sees that this queue is always non-empty and there are processes starving, it will try to change their priority just to get them some CPU. All of that is built into a scheduler to avoid starvation.
New process comes to what queue? Like Q1, like highest priority, or like
New process you don't know anything about, so you give it the benefit of the doubt. It starts here, and after its first time slice, you observe what it did. If it did IO, it will stay there because you're already at highest priority. Otherwise, it will keep dropping.
and the ones which are waiting in IO, like, and they come back, they are like they are given the higher priority or the same priority which they were.
Yeah. So if you are here, you do IO, you go out of the queue, and then when you're done with IO, you will rejoin because you did not use your CPU time slice. Okay, so you cannot get any more priority than one, so you will rejoin there. Other questions? Okay. So that's process scheduling. Let me talk a little bit about threads now, so that you can have some sense of what threads are and how threads work and so on. Okay. So I'm going to redraw that picture I drew earlier of a process and its address space. Okay, I assume many of you have at least heard or used threads, but we are going to look at that in a little more detail here. Okay, so this is the process address space that I had drawn. Okay, so this is your code segment, this is your stack segment, this is your heap segment. Okay, and that's the memory layout of a process. Okay, in the code segment you have code. Okay, you typically have machine code, but let me just write some pseudo code. Okay, so these are just statements you have in your program. Okay, what we mean by a traditional process, or a single, or is also referred to as single-threaded process, is essentially an address space which has a single stream of execution woven through it. Okay, what that means is at any given point in time, okay, there is one stream of execution, and that is actually executing a specific statement within your code segment. Okay, once you execute this statement, you're going to do sequential execution, go to the next one. If there are loops and so on, you're going to jump, or you call function. Okay, that's what a traditional process looks like. So this is your program counter. Okay, so that's basically a register that tells you which instruction is getting executed. Okay, the single-threaded or traditional process. Okay. Now, when you generalize this to a notion of a thread, you get what is called a multi-threaded process. What essentially has happened is you take this picture and you generalize it and say, we'll actually make this a little bigger. So if you allow multiple streams of execution, okay, to share an address space, you get what is referred to as a multi-threaded process. So what does that mean? So what that essentially says is, if thread 1 is executing this part of the code, another thread can independently execute some other part of the same program. Okay, so thread 2 might be executing function foo, thread 1 is in function main, thread 3 could be executing yet another function. They are all concurrent. Okay, each thread is independent of the others in terms of actually having its own program counter. Each thread will also have its own stack. Because if you have local variables here, you push them onto your stack. There's no such thing as a global stack. This process, this thread rather will have its own stack. Stack 1, stack 2, you'll have stack 3 and so on. Okay, the heap will still be shared by all the threads, but each thread will actually have their own program counter. This PC1, PC2, which points to what statement they are executing. Okay? So there are multiple threads that are executing different parts of the same process all at once. Okay? This is referred to as the notion of a thread. Okay? So flow of control to an address space. Each address space can that's an address space. Okay? Each address space can have multiple concurrent flows, and the thread has access to the entire address space, which means that global variables, all the threads have access. They have their own stack, but they all share global data structures. Okay? So this can give you potential. It certainly gives you higher concurrency. If you have more than one core, you will get true parallelism as well. Okay? Because you can have one thread actually run on core 1 and another thread run on core 2. Now this process is being executed on 2 cores simultaneously. There's true parallelism. So you will get that as well. Okay? And you might need to implement synchronization whenever you have multi-threaded applications, whenever you have access to shared data structures. You will need to implement synchronization, locks, semaphores, monitors, stuff that you may have heard of. You will need to implement because you don't want 2 threads to go access the same data structure at once without synchronization. That may corrupt your data structures. Okay? So that's the notion of, just a second. This is the notion of a thread. Okay? So here's a picture of what I just showed you. Okay, that's a slightly different picture. It's showing you 3 threads. Each of them have their own program counter and of course their own registers, which I didn't mention. Okay, and they're all executing different parts of that address space. Okay? And then you have each of them have their own stack. They'll share a heap and so on. Okay, same picture shown slightly differently. Okay? Now, assuming we sort of take that, let's look at the threads in a little more detail. Why would you want to use it? What does it give us and so on? Okay. Threads are multi-threaded processes are very useful whenever you have, even in a single core system, but whenever you have more than one core, they give you true parallelism. As the number of cores of machines or servers keeps increasing, in order to use all your CPU resources well, it is better to take your applications and make them multi-threaded. Okay? That way they can use their CPUs. If you are single-threaded or a traditional process, it can run on only one core at any given time. If you have 16-core machine, the other cores are going to be unutilized by this process. Of course, if there are other ready processes, they could run them. Okay? But this process, each process that single-threaded can use at most one core. Okay? But if you make the processes multi-threaded, you can make good use of all the CPU resources. Okay? That's one advantage. Another advantage is if your application is actually distributed. Okay? Switching between different processes of the same application, same larger application, may incur higher context switch overhead. Okay? Switching between threads of a process is much cheaper because they share the same address space. You're simply going to have to save the registers and load new registers. Okay? That's much cheaper than switching between processes where you have to save the entire memory management information like page tables and whatnot, and then program counters and registers and all these other things have to be saved and restored. So switching between processes is a heavyweight operation when you do CPU scheduling. Okay, when you switch from one process to another, that's more heavyweight. Switching between threads of the same process is much more lightweight. Okay? So this can make better use of your resources if you have multi-threaded processes. And so that's context switches. And as I already said, you can have avoid per process overhead. Also, thread creation, thread deletion, etc. is much cheaper than process creation and so on. Okay? If you create the process, the OS has to actually look at the binary of that process that may be programmed that's sitting on disk, has to load that process into memory, set up an address space, and so on. That requires quite a lot of overheads or involves overheads. On the other hand, if you have a process here, okay, starting another thread within that process is a very lightweight operation. You only need to essentially allocate a new stack within the process. It's already loaded in memory. You just allocate some region saying that's the stack and give it its own set of registers. Okay, and then your thread has been created. Okay. So thread management, okay, is much more efficient than traditional process management. So when you have large applications that need lots of different modules, building them as threads will actually give you lower overheads in your system overheads. Right? If you have processes, okay, you have to partition them into independent processes, there will be higher overhead. That's the takeaway there. Okay? Threads also have full access to the address space, which makes some things easier, but also makes other things harder. We'll talk about that. And you get true parallelism as opposed to single-threaded process. I already mentioned that. Okay? Yes.
So this thread scheduling is similar to process scheduling?
Yes.
It's the same ready queue and
Yes. So thread scheduling and process. In fact, what happens in the kernel is, as we will see in just a moment, if you have what are referred to as kernel level threads, okay, you are actually scheduling threads, not processes at that point. Okay, because a single threaded process is just assumed to be one thread within that process. So you are just given a pool of ready threads, not ready processes. You just generalize the CPU schedule. Okay. So same policies, nothing has changed except that you are scheduling threads at the kernel level rather than scheduling processes. We'll talk about that in just a moment. Okay, I just wanted to put this up just to show you. This is just a list of all the active processes on this laptop, but this column here, okay, is showing you how many threads are associated with each process. Okay? You don't have to look at the numbers except that to say that most of them is greater than one. I was going to tell you that most common applications that are being developed today are actually multi-threaded. Okay, so you see here, there is Skype and there's Dropbox and there is Mail and PowerPoint or whatever is gone, but they are all multi-threaded. Okay, so they all use multiple threads. Browsers are multi-threaded. So most of the applications have become multi-threaded because your machines are multi-core. So to make effective use of all your resources, it's better to build them that way. Okay, so that's something to keep in mind. Yes.
so in case of multi-core processors, the process scheduling algorithm also decides which core to give the
Okay.
job.
So question is, if you have multi-core systems, how does the CPU scheduler work? So what we talked about today were all uniprocessor, which means single core, single CPU. Okay? I have not talked about multiprocessor scheduling. That's coming next class. Okay? Because that requires us to change certain things. It doesn't generalize. Going from processes to threads is an easy change in a uniprocessor world. Going from one core to multiple core is a much bigger change. Okay, so we will see different kinds of scheduling algorithm next time. Okay, today we are just doing a recap of uniprocessor world. Okay, so yeah, that's coming, but that's different. Other questions? Okay, so let's talk a little bit about different kinds of threading models. So I talked about single-threaded process already. That's your traditional process. Okay. It uses blocking calls. Okay. All I/O is blocking. Whenever you do any I/O, you basically stop executing. You go into the wait queue. I already mentioned that. When your I/O is done, you come back. Okay, and there's no parallelism. Okay. If you have multi-threaded process, you also have blocking calls. Okay, but if a thread does an I/O, only that thread is blocked. Okay, other threads of that process can run so long as they're kernel level threads. Okay, so assuming that the kernel is aware of this thread, a blocking call by a single thread doesn't block the whole process, it only blocks that thread. Okay? This allows other threads to continue to execute and make progress even though this thread is gone off to do I/O. So you can make more progress as a result. Okay? So that's a multi-threaded process. Okay, between these two models of a single-threaded and a multi-threaded process is another one which is essentially an event-based model. It's called finite state machine event-based model. This model uses a traditional single-threaded process, but it uses non-blocking asynchronous calls throughout. Okay? All I/O is non-blocking. Okay? What that essentially means is if you make an I/O call, you're not going to block while this I/O is pending. You're just going to issue this call to the OS and say, go execute this I/O, okay? And then interrupt me later when done. And then the process can continue to execute. Okay? This requires you to actually change how you implement I/O. It requires you to change the code in your system. It requires you to have event handlers. Okay? Because you sent off an I/O request, you're not waiting for it to finish. You've gone off starting to compute something else. When your original I/O finishes, you will be sent an event or a signal which will tell you your I/O is done. You need to implement an event handler that goes back and says, why did I issue this I/O? How do I now handle that? The fact that it's done. Okay? So it requires you to write your applications in a very, very different way, in an event-based manner, okay, and use asynchronous calls. Okay? But it does give you the same advantages, okay, that a threaded application gives you, which is you don't have to wait when an IO request is sent. You can actually continue to make progress, which is essentially what threads also allow you to do. If one thread blocks, other thread makes progress. Here, if there's one outstanding IO request, the process doesn't block, it can continue to function. Okay? So this is something you typically may not have encountered. You may have written threaded applications, you may have written single-threaded applications, but typically applications that do asynchronous I/O, they are much more complicated to write. They do exist, okay? But they do have some advantages and disadvantages. We'll come back to this at a later point. I just want you to keep this in mind, saying we have actually only looked at 2 of the 3 models. Okay, when we talk about web servers and so on, I'm going to bring that back. Okay, so that's all about threads. What threads are? I'm going to give you 2 examples from a little bit more realistic applications to understand how you might use threads. The first example is a web browser. Second example is going to be a web server. So let's say you want to now write web browser as an application. It's not a distributed application. It just runs on one machine. But be that as it may, question is how could you use threads to modularize the application? Okay, so typically, if you have a browser, you will see what kinds of tasks does the browser perform. Okay? You might have to have a GUI associated with the browser. Okay? So there's all sorts of graphical user interface stuff. So that's one part of any application. Okay? And then the processing involves whenever you click on a link, okay, your browser has to make a request, send it off to the web server, wait for data to arrive over a network. Okay? Once the data arrives, let's say it's an HTML page. Okay? You have to process that page. Okay? You have to parse it. Okay? Maybe your page has embedded images. Okay? You only downloaded your HTML at this point. So then you have to take each image, set up connections to the server and download each of those images. Okay? Once all the images have been downloaded, you have to then render them. Okay? They might be in different format, JPEG or PNG or whatever. You have to decode the images and display them. Okay? And so on. Yeah, so any browser has to perform a whole set of these tasks. Okay? Handling user events like user clicks, communicating with remote servers, data that's come over a network needs to be processed, you may need to fetch additional data, and all of that has to happen before you can display the page. Okay? So now the question is, if you have all of these tasks, how can you use threads to make this browser make more effective use of its resources? Okay? So this page is going to show you a very simple way, sort of conceptual way, to design a multi-threaded browser. So you could say you have a thread that is designed, whose task it is just to look for user clicks and so on. Okay? You can have another thread that is responsible for setting up connections, for doing the networking part of the browser. It sets up connection to the web server, constructs HTTP requests and sends them off. Okay? You can have yet another thread that is going to parse HTML. Okay? You have to understand HTML and then parse it. Okay? And then if you have multiple embedded objects, you could have one thread each doing parallel downloads of all these images. Okay? Maybe there are ads, you can make a thread for an ad and whatnot. Ad server to download that image and so on. Okay? So if you partition the task of a browser and have threads do each small piece of what the overall browser does, then you got a multi-threaded browser. Of course, you could have had a sequential browser, single-threaded. Okay? It would perform all of these tasks sequentially, okay, which might substantially slow things down. Okay? You can imagine you click, your browser, single-threaded browser goes and fetches the HTML. Once the HTML comes, maybe there are 20 images in there. It's going to then fetch each of them sequentially. Okay? Nothing can be done until all of that data has been downloaded. The user is sitting waiting for the page to load. The browser is churning one image after another, getting them all. Then it's going to process them all and finally display. Okay? That's going to slow things down. From a user's perception perspective, it look like a very slow browser. Okay? On the other hand, if you had multi-threaded browser, you can have each part of the document be loaded in parallel. Okay? Maybe the HTML comes and it's immediately rendered, and as each image is downloaded, you can start displaying that image. You can actually see this happening. If your connection is a little slow, you can see them all happening in parallel. It's because each of these things are being fetched by threads and whatnot. Okay? So that's a way you can actually build a browser that is seen by users as being more responsive. Yeah, so in this case, making it multi-threaded has helped, yeah, in terms of user thinking the browser is faster or better or whatever. Okay, and of course there will be other threads that might do things like JavaScript processing because the image, the HTML might have JavaScript embedded in it. So there are lots and lots of things. Like you might have Java applets and then you might need to load Java and all of that kind of stuff. Okay, that's one example. Any questions on this? Yes.
When you have multiple threads, want to download that multiple things, and but you have limited bandwidth, so you need to decide which thread to do the job first. So this is scheduled by the browser, or the browser just send a request to the OS, and OS schedule the.
Yeah. So the question is, you might have multiple threads. You're trying to download multiple images, but you may be bandwidth limited. You may be on a slow connection. Who decides which threads get to download what in what order? Yeah, that's your question, right? So typically the browser is not responsible for managing network resources. Okay? The browser may have multiple threads. It might then send off multiple requests for multiple images. Okay? Then all these requests are going to be all outstanding, and you're going to be downloading this data in parallel. Okay, so that is being handled by the network subsystem of the kernel. The kernel will basically, everything will slow down because TCP will say I don't have enough bandwidth, so you'll just download it slower. Okay, but the browser is not that intelligent to say it's a slow connection, let me do things sequentially. You could build a browser that way, but most browsers don't do that. They just leave it to the OS because some machines will have better connectivity than others. Okay. Yes.
So different threads, do different threads have different priorities?
Do different threads have different priorities? That is up to the browser, of course. Typically, when you have threads within a process, you treat them the same. Okay? The process itself might have different priorities. It's not to say you cannot accord more priority to certain threads, but in this case, there doesn't seem to be a particular need to say this thread has higher priority than the other. There may be other applications where that may be true, but not necessary here. Yes.
In case of multiple tabs, does each tab has different priority?
Okay, that's a good question. I was going to come to tabs in just a minute. So that was another reason you might have threads. So if you have a browser with all these tabs, you can also have a set of threads assigned to each tab. Okay, so if you are reloading this page or the page auto refreshes every 5 minutes or whatever, there are some threads that will do this and some threads do that and some threads do that. Okay? As far as priorities and all go, you can decide whether that's important or not. Okay? Now that's a multi-threaded design. Okay? If you look at a browser such as Chrome, okay, Google Chrome, it doesn't necessarily use that model. What it actually does is each of these tabs is given its own process. Okay? Within that process, there may be multiple threads. Okay? And the reason that Chrome does this is security. Okay? Because it may be that this tab has loaded a page that has some malicious JavaScript in it. Okay? And in this tab, you're logged into your bank account or something like that. Okay? Now, if these are all part of the same process, every thread within the processor has access to the entire global address space. So you can see what is being done in this tab by a thread in this tab. Okay? So now if you make this tab its own process and this tab its own process, these threads cannot see what's going on there because you cannot look into another process's address space. You can only look inside your own address space. The OS doesn't let one thread go and see what another process is doing. Okay? So Chrome, for security reasons, has adopted a hybrid model where these tabs actually are their own processes. Within those processes, you can have multiple threads to get your thread level parallelism. But across tabs, you have actually a firewall in terms of not a network firewall. I just use that in an abstract way. But you basically prevented threads from one tab looking at what's going on in another tab. Okay, so that's a model that Chrome has adopted. Other browsers don't do that. They just have one global pool of threads. Okay, other questions here? Okay, so now I'll talk a little bit about servers. This is a multi-threaded server. Okay? I'm going to use a web server as an example, but this model is going to work for many different kinds of servers. Okay, so you can say we know why to make a browser multi-threaded. Now let's look at the server and say why should a server be multi-threaded? To understand that, you have to figure out what does a server do. Okay? Typical servers like a web server are going to basically sit and wait or listen for network requests to arrive. Okay? They're going to wait for clients or browsers to send them requests. Okay? Once a request comes in, they're going to process that request, okay? Construct a HTML response and send it back. Okay? Or it might be just a request for a JPEG image. In that case, you are going to send the JPEG image over HTTP. Okay? So browsers are going to be receiving requests, not browsers, servers are going to be receiving requests over a network. They're going to process the request and send back responses. Any server is going to do this. Okay? The question is, what happens if multiple requests arrive at the same time? Okay? User 1 sends off a HTTP request to load a page from server. Okay, another user also sends a request to the server. If the servers were a single-threaded sequential process, you would be processing these requests sequentially. The first request will be processed. While it's being processed, the second request will just come and wait, because there's nothing you can do here. You have a single thread, so it can only do one thing at a time. So it's processing request 1, request 2, request 3. They'll all come and wait. Okay? And then once request 1 is done, you'll take the next request from the network queue or socket and then process the next request and so on. That's going to lead to pure sequential processing. Okay? It's going to also cause users to wait longer because your requests are just going and getting queued up at the server and the response will take a while to come back. Okay? You could have a multi-threaded design, which is what is shown here, where you can use what is called a thread per request model. Okay? In a thread per request model, every time a new request comes in, you spawn a new thread. Okay? You say request came in, create a new thread and say go service that request. Okay? So if more requests come in, more threads get spawned and they all serve the requests concurrently. If you have multiple cores, you will run on multiple cores and you will basically be able to achieve some notion of degree of concurrency or parallelism. Okay? So in a thread per request model, you are going to essentially dynamically create a thread every time a new request comes in. And once the request is done, the thread will be terminated. Okay? That's one way to make a multi-threaded server. Okay? And that's often done as well. Okay? Another way to build a multi-threaded server is you don't create a new thread every time a request comes in, but whenever the server starts up, you create a pool of threads and you keep them alive the whole time. Okay? Let's say when server starts up, you create a pool of 10 threads. Okay? That allows you to give a concurrency of 10, which means if 10 requests come in at the same time, all of them can be serviced. Okay? If a 11th one comes in when 10 are busy, then that has to wait. Okay? So you have to decide what is the degree of concurrency your server supports, and let's say you pick a number n. So whenever your server starts up, you are going to create n worker threads. Okay? So these are the worker threads. There's also going to be a master thread that is waiting for requests. Okay? Whenever a request comes in, it looks for an idle worker thread and hands the request to the worker thread and goes service. Okay? Once that worker thread is done servicing, it rejoins the idle pool. Okay? So the number of worker thread determines how much parallelism or concurrency you are going to get. In a thread per request model, that will vary depending on how many requests are coming in the system. If you're busy, you will have more threads. If you're not busy, you will have fewer threads. Here, your static pool of threads that you create at startup time. Okay? So if you look at the design of the Apache web server, which is a very popular open source server that you can use, many websites use Apache, it uses this model. Okay? It uses a pre-spawned pool of worker threads. You can define how many worker threads you want in a configuration file for Apache. Okay? The default is 10. If you don't say anything, the default configuration parameters are create 10 worker threads. Okay? But you can change that if you believe your website is going to be busy or not. You can change that value. Okay? That's the default. Now Apache is smarter than just creating a static pool in that if it sees that there are more requests getting queued up, okay, it will increase the size of its worker pool. Saying there are more requests coming in, 10 is insufficient to service this request rate. Okay? So let's spawn a few more threads. So then it will basically increase the size of the worker pool on the fly. Okay? And then on the other hand, if it sees that there's a lot of threads idling, not enough requests coming in, it may reduce this workers pool size. Yeah, so Apache has not a pure static model. It basically is static for some periods of time, but every so often it will reevaluate based on the workload that is being seen in the system and change the size of the worker pool accordingly. Okay? So that's basically how a web server is going to use threading to efficiently serve requests that are coming. Yes,
What's the disadvantage of having a pool size too large?
what is the disadvantage of having a pool size? That's a good question. So, one question is why bother, or you ask that question another way, why bother having a pool that is being changed on the fly? Why not decide what is the absolute maximum size of the pool and just pre-spawn that when you start up? You could say 500. Yeah, and so whenever process starts, let's start 500. What's the disadvantage? Yeah, that's the question. So whenever you have these idle threads, okay, they are going to consume system resources. Okay? You will have to have stack allocated for it. You will have to have resources allocated for it. They may be simply idling. The CPU scheduler has to keep track of them, and so they essentially waste resources. Okay? Now, if you have resources to waste, you could do that. But in many cases, if you want to use your system resources efficiently, right, you don't want to have a gigantic pool of threads which are just sitting there idling, doing nothing, and then your memory size of your processes become very large. It's just consuming lots of resources that are not being used in the system. Okay? So the only downside of not doing that is it wastes resources. That's all. There's no other reason. So this is just making more effective use of resources. It's only taking more resources when you have to. Okay. Any other questions? Okay. So I'm going to talk a little bit about thread management in the next 5 minutes, and then we will stop. So we'll talk about different kinds of threads, and then in that context, creation, deletion of thread management, and so on. And then the first kind of model we are going to see is what is called user level threads. So there are two kinds of threading packages: user level thread packages, kernel level thread packages. So we'll just talk about the differences between the two. Okay, so let me see. I thought I had a picture somewhere. Okay, so I'll start with the picture, then we'll go back to this slide. So what happens in the user level threads package is threading support is built using user level libraries. You do not use any OS features to implement threading. Okay? Threading is entirely built in libraries, okay, without any support from the operating system. Okay? Here's a picture that's being shown here. So from the OS's perspective, the OS is not even aware that the process actually has threads in it. It looks at all processes as single threaded process. Okay? Or it assumes that all processes are single threaded process, and then when it picks a process to run, okay, because that process actually has threads in it, there is going to be a second level scheduler called a user level library scheduler. Okay, so the kernel is going to pick a process to run. Once the process runs, the library is going to run its own scheduler saying the process is now running, which thread should we actually execute. Okay? And then it's going to pick one of its threads to execute, and that's the thread that's actually going to run. Okay? So if you have user level threads, scheduling is a two-level decision. Okay? The kernel picks a process, and the library picks a thread within that process, and that's the thread that's actually going to run. Okay? So this is what is referred to as a user level threading packet. Okay? The advantage of user level threads is basically there are many advantages. One advantage is you don't need any OS support. So if your OS did not come with threads support in it, you can still write applications which have threads in them by just getting the right libraries, okay, and then just linking those libraries to your application. Okay, so there are some OSs that don't have threading support. If you want to run multi-threaded code, this is the only way you can do it. Okay? Furthermore, because threads are managed by the library which is inside the process, thread management is going to be very cheap or very efficient. Because thread creation is a call to a library function. It's a function call, okay, not a system call. System call requires you to go to the OS and ask the OS to do something. System calls are more heavyweight than function calls within your process. Okay? So create thread is actually going to go to the library and ask it to create a thread. No OS involvement is necessary. Delete thread is going to go to the library, ask it to delete a thread, and so on. Okay? So thread management is much cheaper in this case. Okay? The other good advantage is you can pick across different libraries that give you a range of implementations. In particular, different libraries may have different scheduling policies built in them. Okay? So you can say this application needs round robin. Okay? So you can pick a threads library that gives you round robin scheduling. Okay? So independent of what the OS does, your threads are now getting round robin treatment. Okay? This other library may say I do lottery scheduling for its threads. Okay? So you can basically have different library schedulers implement different policies. They can all coexist in the system. So the designer, application designer, has a choice of what scheduling policies for its threads makes sense for that application and pick it accordingly. Because it doesn't require you to do anything with the kernel. Kernel is going to implement whatever CPU scheduling policy it wants at the process level, but at the thread level you have flexibility. Okay, so that's going to be all the advantages of user level threads. So there are some disadvantages as well, but let me see if there are questions.
So, so if a process spawns a thread, so there are ultimately two threads, right? Or is it, how is that?
So the process starts up, it will start with one thread. That's main, that's just executing main.
The main.
You create a thread, you will have a second thread, then you have two threads in the process. Yes.
So the library scheduler basically has two threads which is running.
The library will know, scheduler will know what is happening. Yes, so here there are two threads. This could be the initial thread you started off with, the second thread that was created. This one has three. Okay, so whenever you do thread create, it will go spawn additional threads. You always start with one thread. That's the one. Every process has to start with one. Okay. Yes.
Is it possible to have user level threads even when your kernel is capable of giving you kernel level threads?
Yes. The question is, can you have user level threads when you still have kernel level threads? I'll show you a hybrid model 2 slides from now that will be exactly that. Okay, it's the most complicated of the lot, but you can actually do that. The other thing to keep in mind before I move on to kernel level threads is that you have what is called many-to-one mapping. Many user level threads map onto one thing that the kernel is aware of, which is the process. Kernel only knows that there is a process. It doesn't know whether the process has threads or doesn't have threads. It just treats it as a process. Okay, so many threads get mapped onto one thing that this kernel is scheduling. Okay, so this is also called a many-to-one mapping.
So then how is performance improved using threads? So when processor is knowing that there is only one process, so like how is it different than running a single thread?
Okay, so that I was going to talk about disadvantage. So a disadvantage of user level threads is because the kernel doesn't know about the presence of threads. In this case, you are not going to get true parallelism even if you're two cores. Here, you are shown two cores. Okay? This process, as far as the kernel is concerned, can be only scheduled on one of those two cores, even though it has threads in it. The kernel doesn't know about them. Okay? So you are not going to actually get true parallelism. You will get concurrency the same you would have got in a uniprocessor world. Okay? You could still have multi-threaded processes running on a single core. You still get modularity, all the advantages we were talking about, you may still get. Okay? So it allows you to run multi-threaded code on systems that don't have threading, but your user level processes are not going to get advantage of true parallelism. Furthermore, if one of the thread does I/O, the entire process is going to block because the OS doesn't know there are other threads, so it will just assume the process did I/O and just block the entire process. Okay, so there are some disadvantages. Yeah. Now let me show in 2 minutes that I have, or maybe 1 minute. Kernel level threads is the exact opposite of user level threads. These are threads that are implemented at the kernel level. The kernel has provided explicit support for the presence of threads. Okay? So the kernel knows exactly how many threads are within each process. It is involved in the creation of the threads and management of the threads and so on. Okay? So in this case, thread creation involves a system call. It's more heavyweight because you have to tell the kernel this process needs another thread. Create one for it. Okay, so it will go create a thread. Okay? It will keep track of all the threads inside the kernel. Okay? So here you are explicitly scheduling threads, not scheduling processes. You pick a thread to run. and the thread is just part of some process, and that thread runs. Okay? So what happens in this case is all the advantages we've been talking about for user level threads are going to become disadvantages and vice versa. Okay? So thread management is more expensive because they involve system call. Previously they involved function calls to a library. Okay? You are going to be bound to whatever CPU scheduler is implemented by the kernel. The previous case, the library scheduler could pick whatever it wants. Here you cannot. You are actually going to be stuck. If you did multi-level feedback, that's what scheduling you're going to get. You can't change that. Okay? But on the other hand, if one thread blocks, other threads can still run. In the previous case, the entire process blocked. Okay? Also, you will get true parallelism. These two threads of these processes are mapped down to two kernel level threads. They can actually shown here. You have 3 threads here. Okay, of which 2 are actually running on 2 cores or 2 processors at the same time. So you are getting true parallelism, which you did not get previously, because the OS didn't know of the presence of threads. So everything we said was an advantage has become disadvantage and vice versa in this case. Okay? This requires the OS to implement threading support. Okay? So the OS will know how many threads are in a process and explicitly schedule a thread and whatnot. Okay? It's kernel level threads. I'm going to just show one picture because there's a question, but we'll come back to it next time. So there are hybrid models as well. Okay? They're referred to as lightweight processes, where the kernel is actually aware of the presence of threads, but then you can also have library schedulers to manage your own threads. Okay? And then you can figure out how to map user level threads to kernel level threads and so on. Because we ran out of time, I just wanted to put this picture here, but I will talk about it next time. Otherwise, we'll just use more time here. Okay, so let's stop here today.